Hi everyone, today we're looking at lesson 2 of unit 6 on the Pythagorean theorem. And today's lesson is broken into two pieces. The first is from module 3, lesson 13. And this is going to be about proving the Pythagorean theorem using right triangles. And I'm just folding my paper in half because when you do a proof, it tends to be very vertical. You need a lot of space to continue each step. So I'm actually going to do Module 3, Lesson 13 on the left-hand side and Module 3, Lesson 14 on the right-hand side, which is going to be a converse proof. So the first proof that we're talking about has an objective that says students practice using the Pythagorean theorem to solve for lengths of missing sides. And so this is going to be a proof by right triangle and similarity. So I'm going to start out by drawing a right triangle, and I'm just going to use a straight edge, and I'm going to do my base and my second leg and the hypotenuse, and I'm going to label this triangle A, B, C with my right angle and opposite side lengths labeled ABC. The next thing I want to do is build an altitude from angle C to the line AB and make sure that when it meets, it forms a right angle. That ensures that I have three similar triangles. So I'm going to redraw that small triangle that I just created. And the labels of this triangle are going to be ADC. And then I'm going to do something similar to reproduce that medium right triangle. And this triangle is going to be triangle CDB. And then I'm just going to label the side lengths that I know from my original image. So I have three right triangles. One is the original triangle that I started with, ABC. The second is the smallest triangle, ACD. And the third is that medium triangle, CBD. Now, because I know that these triangles are similar, I'm going to be able to make some comparisons here based on the ratios of the sides. Now, this information is from Module 3, which was our unit on doing geometric dilations and proving similarity of figures. So if these triangles are similar, then according to our work in Mod 3, they are also proportional. So what I'm going to do is compare two triangles at a time. The first ones I'm going to do is ADC compared to ACB. And if those two triangles are similar, then I know that they have proportional sides. So the distance between side AC over side AB is equal to the distance of side AD over side AC. When I simplify with cross multiplication, I get something that is equal to the distance of AC squared equals the distance of AB times the distance of AD. So this is the first piece of information that's going to be kind of critical for my proof. Now I'm going to look at two other triangles. I'm still going to be looking at ACB, but I'm also going to look at CDB. And if those two triangles are similar, then I know the following proportion is true. BA over BC equals BC over BD. After cross multiplying, again, I get a formula that says BA times BD equals BC squared. So I'm going to look at my two equations, that first simplified and the second, and I'm going to add them together. And when I do that, I get AC squared plus BC squared equals AB times AD plus BA times BD. Now what's important to note here is that AB and BA are actually the same thing. So I can factor out that term and say AB times what's left, which was AD plus BD. And then I still have AC squared, which is actually the side length B squared, BC squared, which is the side length A squared, equals, and then I have that distance AB, which is the whole side C, times AD plus DB. So that also is that whole side C. So really I have C times C is C squared. So when I look at the distances of the side and I compare them to the formula, it's clear that I can simplify down to the Pythagorean theorem, which demonstrates that it is true. Then I go back up to the top of my page to talk about Module 3, Lesson 14. This is going to be a converse proof, or we're going to discuss a converse proof. We're not really going to prove it today. Our first objective says students illuminate the converse of the Pythagorean theorem proof through examples and counterexamples. And students apply the theorem and its converse to solve problems. So what we want to think about is just some basic information. We know two unique proofs for the Pythagorean theorem so far. The first one that we know it has to do with squares of equal area. So basically when we have the same square, we can divide it into pieces in a different way and use that information. The second one we learned was about the right triangle and similarity, which is what we just did. The opposite of the theorem is also true. So what we know about the Pythagorean theorem basically says if you have a right triangle, then a squared plus b squared equals c squared when a and b are the legs and c is the hypotenuse. The converse of that proof says if a squared plus b squared equals c squared, then the triangle is in fact a right triangle. So it kind of just flips that statement around, which allows us to solve more equations in a variety of ways.